Good afternoon. Today it's a pleasure to welcome our speaker, Andrew Szentgyorgyi. He is an astrophysicist at the Smithsonian Astrophysical Observatory, and his research activities on optical high dispersion stellar spectroscopy with an emphasis on precision measurement of stellar radial velocities. These measurements are often used to detect and measure the mass of exoplanets, especially the lightest exoplanets with masses similar to that of the Earth. He has exploited a number of state-of-the-art technologies to improve the precision of these measurements, and he is currently the principal investigator of the GMT-Consortium Large Earth Finder, the G-CLEF, first light instrument for the Giant Magellan Telescope. Thank you.
Thank you so much for having me. It's such a pleasure to be back here in Sao Paulo, visiting with my collaborators and colleagues. I was supposed to come in 2019, and frankly, my dog ate my passport the night before I was supposed to leave. So I rescheduled for 2020. It was supposed to be March 2020. When I was sitting in the airport, I was starting to wonder what curse would befall me and keep me from coming here. But here I am, and it's so great to be back with my friends. So today I'd like to tell you a little bit about a search we're going to do using an instrument that we're building for the Giant Magellan Telescope of mutual interest to everybody in the room. And I'd like to start out with this picture. Now, if you saw my talk in 2017, I think I used this picture, but I love it. Because if you're an alien and you fly over the surface of the Earth, and you look out the window of your spacecraft and you see what you see in this picture, you know there's life on Earth. And it's not because you see the lights from the people, houses, towns, cities, because that could be anything. It could be volcanism. It could be the residue of a asteroidal impact that's still glowing. But you would see this deep, deep green glow and a faint red glow. And that would tell you there's life on Earth. It would tell you there's life on Earth because the Earth's atmosphere is 21% diatomic oxygen. And that's only there because of life. Now, if you're an astute student of this, you know that, move this just a little bit. Okay. You know that they detected a faint auroral green glow on Mars from the dissociation of carbon dioxide in the Martian atmosphere, but it's very, very faint, and they've had to search for a long time to see it. Anybody who lives close to the poles, as I do relatively, on a good, clear winter night when the sun is active, go outside and you can see this from your house. So, the structure of this talk is as follows. First, I want to talk to you a little bit of why I believe O2 is such a good biomarker. Why search now? You know, why didn't we search a long time ago? Why shouldn't we wait a long time? Then talk a little bit of how to find a biomarker. A little bit about the Giant Magellan Telescope search strategy. Another Pathfinder search that we plan to do using the Magellan telescopes in the atmosphere of Proxima Cen-b. And a little bit about the James W. Webb Habitable World Observatory context. So, O2 is a biomarker. Now, there's only so much oxygen in the Earth's atmosphere. This is a picture of actually my colleague Tanya Bosek showing a bubble of oxygen being respirated by cyanobacteria. And so plants on Earth take the solar energy and various chemicals available to them, process those chemicals, and respirate oxygen. If you killed all the plant life on Earth, that 21% balance would be reduced to sub 1% in a very short period of time. The 21% balance of O2 in the Earth's atmosphere is very much a non-equilibrium composition. And again, only due to the fact that there's plant life on Earth. Good thing, because we like to breathe oxygen. If you look at the history of the Earth's atmosphere as we understand it today, What I plotted here is time from the beginning of the Earth as we understand it to today in gigayears, and then log mixing ratio of different compositions of the Earth's atmosphere. And in the beginning, it was very, very hot. We don't know much about it. The Earth had to cool down for about half a gigayear. But then sometime around 4 gigayears ago, continents formed. We believe continents are important. We believe liquid water is essential. We believe that O2 is evidence of life. And we also believe that an ocean world, the various chemicals we believe will constitute life anywhere in the universe are too dilute to actually start to form interesting molecules that then move up the chain of complexity until they become amino acids, DNA, RNA. And so you need lakes because you have to take surface water, put it in a hole, evaporate off a lot of the surface water, concentrate it into a soup that's rich enough to make those chemicals. So the birth of continents is indeed a very important thing. Shortly thereafter, these beasts called stromatolites appear. We see their fossils. They're very, very primitive animals, more primitive than blue-green algae. They grew in big clumps, and the fossils are quite evident. And they start to actually produce oxygen. They also start to produce methane, and they start to affect the composition of CO2. The thing is that plant life is sort of evolving between the arrival of the stromatolites in 2.5 billion years ago, but there are all these sinks for oxygen. Silicon likes to attach to oxygen and make sand. Iron likes to attach to oxygen and make rust. There are all kinds of things that as plants produce oxygen, they're eating it up. But then something like 2.5 gigayears ago, all of a sudden the sinks are probably filled, and you start to see oxygen-based molecules form. The predominant one is diatomic oxygen. We produce some ozone, some N2O, and those balances increase somewhat at the expense of CO2 all the way up to the present, to the Cambrian. Of course, Cambrian is when life forms as we sort of know them, motile life forms with visual capability start to form to the present, where we now have 21% oxygen in the Earth's atmosphere. And so we have already detected exoplanet atmospheres. We detected, in some cases, their molecular constituents. But we do believe that O2 is unique to life, and the detection of ozone or diatomic oxygen would be strong evidence indeed of life on an exoplanet. Now, I had an idea that we always think about absorption. I mean, those of us who do this sort of business are trained as stellar physicists, and all spectra are absorption spectra. But of course, if you're a spectroscopist, you know that there's this terrible feature at 5577. When you take a ground-based spectrum and reduce it, the first thing you have to do is take some software tool and cut that piece of the spectrum out because it entirely contaminates the spectrum. And so there are a number of other emission features in the Earth's atmosphere, but 5577 is a visual band is the biggest one. And I thought, what a great idea. Instead of looking for absorption of oxygen, diatomic oxygen in the Earth's atmosphere, why don't we look for emission? And I thought I was a very clever lad until I found a paper called The Pale Green Dot by Luger et al. And he actually did, I tried to calculate this. It's very, very hard because you have to take aeronomical data and convert it to data that makes sense to an astronomer. And astronomers use all kinds of crazy units. And so I calculated for a while, and I got a number that it took something like 10 to the 5 hours to collect a 3 sigma signal. So I was not enthused. And then when I found the Luger paper, they're a little more optimistic. The real important thing to look at is this panel over here. Where did I lose where's my cursor? Over here. And the thing that really determines how long it takes to get up to some significant result is the contrast that you have between the host star and the planet. And so they consider several different contrasts, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, as a function of resolving power, and then they plot how long you have to integrate to get up to some reasonable detection level, assuming a tenth of a terawatt of 5577 emission from Proxima Cn-b. And if you can work at a contrast of 10 to minus 7, well, things are sort of interesting. You might be able to do it in a couple of hundred hours. But the truth of the matter is right now, we can barely get to a contrast of 10 to the minus 5. So you're at a minimum, you're talking at something like 2,000 hours of observation on a really, really big telescope, an ELT. And it's hard to believe the Time Allocation Committee would ever let you do that. So I gave up on that idea. So here's an idiot's guide to the spectrum of the Earth. And you see over there on the left, that is evidence of diatomic nitrogen and oxygen. It's Rayleigh scattering, and you see that the spectrum, the reflectivity tends to go up. The sky's blue. And then you have some other sort of interesting features. Water vapor is a monster, but water is fairly prevalent in the universe. So finding water would be interesting. I mean, it's good to know that there's water on your habitable planet, but it's not really the smoking gun. There's some other things that are interesting. There's a ozone band, but the killer signal right here is in fact this pushing the wrong button. The real killer signal here is this deep feature at 7,600 angstroms, the oxygen A band. And so I believe that this is the place to go look if you're going to go look for life. So you might well ask, well, what are the different biomarkers you might consider? Anyway, I have a finger, so I cannot. Oh, well, that's not working either.
Your computer is okay.
Oh no, here we go. Okay. Is it happy now? Okay. Okay, here we go. Here we are. I mean, you could fairly ask me, well, what about other stuff? Oxygen is it certainly looks like a good prospect. It's extremely amenable to detection because 7,600 angstroms, it's a good place to work as opposed to, for instance, the near infrared, which is very hard. And there are no identified abiotic pathways. People continually search for abiotic processes that would produce diatomic oxygen. There was one proposed based on CO2 and photochemical reactions, but the obvious question is, if that's a strong pathway, why isn't there more on Mars? There's a tiny bit of oxygen in the Martian atmosphere, but not a lot. Methane's another good thing, and part of the story. If we found diatomic oxygen, or we got a phi sigma result, we'd want to see methane too, because that's also a strong biosignature. But unfortunately, there are all kinds of things that can make methane. So methane absorption all by itself is not the smoking gun of life. Ammonia is another nice biomarker, but unfortunately, it's also present in Jupiter's upper clouds. I mean, it's made other ways. N2O is difficult in Earth's atmosphere. It's only 300 parts per billion. And then when you get down to sort of more complicated things, they're probably undetected. So this is at least, at a minimum, it's the place to start. and they'll look for confirming evidence. So I think that O2, I've tried to convince you that O2 is the first place to look for biotic activity. So why search now? Well, the population, when I started in this business on some particular day in 1995, after Marcy and Butler announced, the only planets we knew about were the planets of the sort we have in the solar system. And now we know there are all kinds of exoplanets. This is a really kind of nice chart of the habitable zone showing the planet's radius and then the habitable zone in terms of stellar flux, but it tells you what different melting temperatures are. I'm sorry, melting temperatures of different molecules are on the surface of those planets. So think selenide, water, CO2, and methane. And so now we have hot Jupiters, warm Jupiters, cold Jupiters, sub-Neptunes. There are all kinds of things out there. We kind of think that the Earth is the right place, super Earths. We kind of think the Earth is probably the right place for life to arise, because we already have at least one example. But it's a rich field now. And in fact, I made this chart a while back, so it's entirely, if I made it yesterday, it'd be out of date. But right now, there's something like 6,000 exoplanets. And the most important thing is that there's slightly more. There are, I think, 500 test planets. There's a huge catalog of things that need confirmation. About, I think there are 5,000 right now. TESS is still, by the way, running. And the thing that's important about the TESS catalog is if we're going to do this work and we're going to search for biomarkers in exoplanet atmospheres, they have to orbit bright stars. We need good signal to noise. It's going to be a very subtle signature. And so the Kepler mission, which found lots and lots of exoplanets, unfortunately are all faint. I think they peak somewhere around 12th magnitude. The TESS exoplanets are all really, really bright. So they're a really good place to look. So the statistics right now, I think, are very favorable, or at least for, if not a successful biomarker search, something like a definitive search. A null result would be interesting of itself, and I think we could produce a null result that would, in fact, be interesting. We have a catalog of bright stars that was required, which we need to search for exoplanet atmospheres, which is the TESS catalog mostly. Statistics suggest that most stars are, in fact, orbited by exoplanets. Most of those stars have Earth-sized exoplanets. Right now, we don't have any true Earth-analogues. And that's part of the goal of the G-CLEF project. We have many exoplanets that are the radius of the Earth. Remember, TESS is a transiting mission, so it measures the radius of the planet, but it does not measure the mass. And right now, at least for a Earth mass planet orbiting a solar-type star in the habitable zone, which is the right place for water to be in liquid phase, you require radial velocity precision of 10 centimeters a second, and we're sort of at a little below 30. We've been making progress all along, and I hope that G-CLEF will, in fact, break through that barrier. Now, most of the stars in the solar neighborhood that would be easy to search are M stars. And the viability of life on M stars is a pretty controversial topic. There's some people that say it's a good place to look for biomarkers. There are other people who say, well, M stars tend to be so active that the radii, and they're easy to find because their orbits are close, they're frequent, they're large the planet is large with respect to its host star, so it has a relatively big signal. On the other hand, because it's close and because M stars are active, there's a pretty big concern that stellar activity would sterilize any exoplanet. So there is a lot of controversy about that. So I think that the search for exobiotic activity consists of the following steps. First, develop a large catalog of bright stars with exoplanets. We've done that. We like to then winnow it down to a fair sample of Earth-analogues. And that means measuring the mass of those planets. If the critical parameter in all of this is the density of that exoplanet. It really needs to be rocky, to have continents, to have lakes. And then finally, to search for atmospheric signatures of biotically produced molecules, biomarkers. So, it's good to look back at the history for a second of how we got where we are. Because when this started out, there was a young Canadian graduate student who came in my office with a senior scientist. And at that point, I was the expert at CFA, along with Chris Stanek, on massive photometry. And he wanted to use photometry to find transiting planets. And I told Dave Charbonneau that it was a ridiculous idea, and he should find something useful to do, like general relativity. But Dave and this Tim Brown went off, and they built the telescope on the left. And in 1999, two groups simultaneously discovered transiting exoplanets, the first step towards studying atmospheres. Dave then had this idea, which he flew by me, and said, well, why don't we try and look for atmospheres? And I said, look, you've already gotten lucky. And so he didn't pay any attention to me, and he operated HST in a mode where he had a filter that was in band for sodium D and out of band for sodium D, and compared the relative size of the exoplanet in and out of band, and it was bigger in sodium D. And it was bigger in sodium D because there was sodium, like the Earth, but there was sodium in the atmosphere of this exoplanet 29548e. It's frankly it's the easiest exoplanet to search for an atmosphere on. It was the first transiting exoplanet. It's got a huge signal to noise. But this is amazing stuff because in addition to finding the atmosphere, it enables that these planets, we can measure the density, because when you use precisional radial velocity to measure the mass of an exoplanet, you don't know the inclination. And so because you don't know the inclination, you actually don't measure the mass of the exoplanet, you measure the mass of the exoplanet times the sine of the inclination. But if it transits, you know that this planet goes right in front of the star, you know the geometry of the orbit, and now you know the mass, not m sine I. This also starts both of these results start a tsunami of transit surveys, Kepler, Corot, TESS, and massive photometry finally fulfilled its promises. And it makes it possible to probe exoplanet atmospheres by comparison in and out of transit spectra, permitting atmospheric retrievals. I'm sorry, so I got ahead of myself on the slides. This is the data from his HST study where he found sodium D in his HST data in 2021. The next sort of step was Dave's group. Heather Knutson actually made a thermal map of a very similar, easy to do exoplanet, HT 189733b, and with the Spitzer IRAC data. And the fascinating result, this is a heat map of the surface of the planet where the line of longitude that bisects the planet locates the substellar point at the equator. And she finds that the substellar point is not the hottest place. The hottest place is the whitest place, and it's displaced in longitude from the substellar point. And what this means is there have to, at a minimum, be circumferential energy transport winds convecting the energy away from the substellar point. That is, this thing is a tidally locked exoplanet, so that means it's convecting heat away. And in loose terms, this is the first meteorology of an exoplanet. Mark Swain then used NICMOS on NIST, NICMOS on HST, to actually look at molecules. This is not really spectroscopy. It's narrowband photometry with resolution of about 40, but nonetheless looking at, again, this 189733b, which is an easy hot Jupiter with a very short orbit. He detects the presence of CO2, water, CO2, and CO. And so he finally actually does exoplanet atmospheric spectroscopy, which is a pretty amazing result. He also establishes an upper limit to the amount of methane, which is a biomarker, and it finds that the temperature decreases with altitude, which is an interesting result in and of itself. Oh, there we go. This is sort of an aside, but it's an interesting result in and of itself. Diane Dragomir looking at a couple of red dwarf exoplanets, discovers that she finds an increased shortward of 500 nanometers, very much consistent with Rayleigh scattering. Whether it's Rayleigh scattering of diatomic nitrogen or oxygen is a purely open question. We can hope. I just kind of like the fact that it tells me that if there are extraterrestrials on this planet, they live under blue skies. And now JWST is doing really amazing stuff. This is a planet orbiting M7.5 and binary, actually. The planet is a big exoplanet. Again, it's a 19.5 Jupiter mass planet. It's also really quite far away from its host star. It's 360 AU. But now, not only are we seeing water, carbon monoxide, you do see some methane here. But the really sort of astounding result, as far as I'm concerned, is the detection of silicates, which is just shocking and sort of indicative of what we can expect from JWST. So how to find a biomarker? Well, as I said, you need a good catalog. So as I said, the Kepler candidates are too faint, but the test catalog, good and bright. So there's a good catalog, a fair sample of transiting exoplanets to look at. We need to measure planet masses by precision radial velocity. We would like to have a true Earth twin orbiting a G2 star, and as I said, that requires 10 centimeter a second precision radial velocity, which we're not quite at yet. It requires something like 5 to 3 or 2 improvement in technique, but it does need better instruments on bigger telescopes that we have today. We need the ELTs. Now, as I said before, low mass stars will be much easier, a fact that both recognized back in 2014 by Florian Rodler and Ignat Snellen, sort of simultaneously. So how do we do that? Well, this is the oxygen A band. This is the oxygen A band modeled for a Earth-like planet at a resolution of 100,000. And the thing that's really quite beautiful about all of this is that you have this very, very specific structure, semi-periodic, but not. It's a fingerprint. It's not just a sine wave. And a technique for detecting these sorts of features has been demonstrated, albeit in a considerably easier system. Ignat Snellen, again going back to this touchstone exoplanet 20945b, was looking for the absorption band of CO. And here it's, well, I think it's clearly detected. He used CRI-RES on the VLT, and what you see in these charts, this is all the data here. Where did it go? Okay, this is all the data. And what you see here is the radial velocity of the spectrum centered on 0 velocity. And what this is it's a layer cake of spectra. And so time proceeds from top, bottom to top. So each one of those, they're I think hundreds. I don't know how many spectra there are in here. And what you see in this data is he's taken, of course, a molecular spectrum has this bandhead structure. He's taken all of the features and sort of piled them on top of each other into one absorption feature to strengthen the signal to noise. But you see this, I think, pretty easily to identify stripe, which moves in with the orbit. So the velocity, the line of sight velocity changes. If you look at it up close, here it is compared with modeling, and it's a pretty neat result. Now, the very interesting feature of all of this is that you can actually directly measure the radial velocity of the exoplanet itself from this data, which is a pretty neat result. So you can learn things about the orbital elements without necessarily transiting. That'll be important for a couple of reasons. The problem is that this is going to be a tough one, because the Earth's atmosphere is only 1% in thickness of the total Earth cross section, and so finding O2 in a transit where you're looking for the light coming through the exoplanet atmosphere, the cross section is pretty small, and so if we could somehow do day-side spectroscopy, what we call reflection spectroscopy, it might be easier because it'll be a bigger cross-section. And I'll talk a little bit more about that now. The problem with, this is from Florian and Mercedes's paper, where they did a very careful study of, they put everything in, you know, the fact that you can only observe at night, that you lose 20% of the observation time at a telescope, and they examined how long it takes to observe diatomic oxygen in an exoplanet atmosphere, given the realities of aperture size, the realities of observing from the ground, and many, many other factors for a volume of exoplanets out to about 20 parsecs. And the sad number they come up with is that to detect diatomic oxygen by the transit method for the Earth orbiting the sun could potentially take 37 years of real time of observation. And to you graduate students out there in the audience, don't sign up for that project. It's not a good one. So this is, they're the first people to realize that probably the best place to be doing is looking somewhere around M5 or something, where if you got lucky, it wouldn't take 12 years, but it might take 8 years. But you're talking about really long observational times. And if you get unlucky, it could take longer or shorter. So we've been working very hard to develop reflection spectroscopy. And you know, the first issue is if I'm an extraterrestrial who happens to be able to see the Earth in transit, the transit happens once a year. And the transit lasts approximately 13 hours. So I wait a year, I get 13 hours of data, and I wait another year and get another 13 hours of data. If you could do reflection spectroscopy, you would be able, you know, you almost can do 6 months a year, possibly even a little bit more, as long as you've got a fair fraction of the illuminated side of the exoplanet reflecting light back to you, you can do science. And so I think that the and you don't have to be lucky. I mean, oh, sorry about that. If you're unlucky, you know, the first 3 transits happen during the day, though you're 13 hours. So with reflection spectroscopy, whenever the object is up, you can observe it. Another very important issue is that in the reflection spectroscopy, the light rays are refracted through the Earth's atmosphere. And you really don't know what layer of the Earth's atmosphere the rays went through. Rays that go deep into the atmosphere are bent a lot. Rays that just graze the top of the atmosphere aren't bent very much. You don't know, and these ray paths will be observable at different times. You won't know which is the right one. With reflection spectroscopy, you know that the light went through the Earth's atmosphere and came back. You know that happened. Went through the whole atmosphere. The other issue is that all the oxygen in the Earth's atmosphere to first order is in the troposphere, the first 8 to 12 kilometers of atmosphere, and some into the stratosphere, but not very much. That's where a lot of the ozone is that protects us from UV radiation. So you are guaranteed with reflection spectroscopy to be sampling that layer of the atmosphere where the oxygen is. You're not sure with transit spectroscopy. So with reflection spectroscopy, you have much larger phase accessibility. You can probably work to more than pi of the orbital phase. It really enhances detectability. The exoplanet, the other thing is you have a bigger sample because the exoplanets don't have to transit. You can do, Ignaz's data was not taken during transit. It was taken out of transit. So you don't have to transit. There's a much bigger sample to look at. You can actually determine the orbital parameters because you can directly measure the radial velocity as a function of time of the exoplanet. The cross-section is much larger because when it's facing, you get the whole cross-section, and you have variable exposures as the year goes on. But nonetheless, even at the smallest sector is visible and reflecting light to you, it's much bigger than transit. And as I said, oxygen is in the troposphere. But the problem is that we've got to differentiate stellar and exoplanetary spectra. And if you just did pure coronagraphy, you would need something like 10 to the minus 10 contrast. And as I said, we're doing 10 to the minus 5 on a good day. So we think that ultimately we could get down to 10 to the minus 7, but it seems unlikely that we're going to get purely down to a contrast of 10 to the minus 10. So what we'd like to do is get to an effective 10 to the minus 10. So to do this, we need to have extreme adaptive optics on extremely large telescopes. So as you probably know, there are 3 extremely large telescopes that are aspired to. The TMT with a 30-meter primary, the GMT with a 25.4-meter primary, and the ELT with a 39-meter primary. TMT's Northern Hemisphere, GMT, ELT Southern Hemisphere, US-led consortium, US-led consortium, European-led consortium. But the instruments that will be available, the TMT is focusing on a near-infrared exoplanet spectrograph. They are still in concept design phase, and they will not be able to observe oxygen A-band absorption. Come on. We are building an instrument, G-CLEF, to do exactly that. And the Europeans have an instrument they're thinking about, but they haven't even gotten really past concept phase. So we're ahead. I think we can definitely do this first. I put this slide in. I think everybody here knows about the GMT. And one important thing that we're going to have on the GMT is an extreme AO adaptive optics system that will operate from 0.6 to 2.5 microns. That sounds like a regular thing to say, but most adaptive optics systems are built for the near infrared, start somewhere about 1 micron, not short enough for oxygen A band. The GMT system goes all the way down to H alpha, and so we'll be able to do this work at 7,600 angstroms. We should have very good resolution, providing great coronography. We will have direct imaging and a high-resolution spectroscopy mode. We've already got a demonstrator operating at Magellan, and again, I just circled the 0.6 meters. So this would be the Pathfinder that we have at Magellan. It will be the first demonstration of optical band AO for this process. So the key science we'll be able to do are planet formation, planet composition, temperatures, atmospheric compositions, cool planets, and searches for life with this instrument. I think you've all seen this. We hope we'll build 2 ELTs. It'd be very nice. We actually, the TMT and the GMT share half the sky. But what we're doing, I'm doing, my team is doing, USP is doing actually, is building this thing called the G-CLEF, the GMT-Consortium Large Earth Finder. It's happening. On the left is my former instrument scientist who's now a professor at Weizmann Institute. On the right is Juliana Garcia Mejia, who is a graduate student who worked with us and is now a fellow at MIT. This is the work of many, many groups. There's Harvard Smithsonian, Stewart, Carnegie, Adolfo Ibanez in Santiago, University of Chicago, the GMT, the Koreans, the Asians have joined us. USP has also been a critical participant with the Steiner Institute. The Israelis have joined us too. And what we like to do is do this Pathfinder search. So the spectrograph will be completed in that thing I showed you will be completed in 2027. And as most people in this room know, the GMT won't be finished till 2032. So what to do? Well, we've negotiated with the Magellan telescopes to allow us to take the spectrograph to the Clay telescope. It has a 6.5 meter aperture. It's on the same site as the GMT, and it already has an extreme AO system working. It provides a unique opportunity to test this new approach for biomarker searches. But then the other thing that's kind of neat is the star that is closest to the Earth, Proxima Centauri, actually has a habitable zone exoplanet that orbits it, Proxen-b. And now Proxima Centauri is a very different kind of star than the Earth. It's a K dwarf, so it's different, and it's not a true Earth 2.0, but it really is a kind of neat opportunity. And oh, I'm sorry, it's not a K, it's a M5.5. Excuse me. And so, in fact, the whole issue of how do we get past this necessity for a contrast of 10, and Christoph Lovis and a bunch of folks at mostly Geneva came up with the idea of how to use the espresso spectrograph with the sphere high contrast imager at the VLT to do something called the high contrast, high resolution technique. And high contrast or high resolution alone only have contrast at 10 to the minus 5. But Christoph makes a very convincing argument that the convolution of these two techniques will provide us with an effective contrast of 10 to the minus 10. And this is something that's very doable at the VLT, which is an 8.4 meter telescope at 7,600 angstroms. So we believe that since the Magellan is a very similar size, we have a very, very, very powerful AO system, that this will make a very interesting search. And as I said, the Magellan AO system is up and running. It was delivered, they started delivering it just before pandemic, and they're almost done. And if you look around for candidates now that you would try and search for biomarkers, this is a plot of the contrast that you would need to find that exoplanet. This is the angular separation of the exoplanet in terms of arc seconds. But the most important thing is these lines, which this is the diffraction limit, this is 2 times the diffraction limit, and this is 3 times the diffraction limit. Now, the system that we have at Magellan works a little better than 2 times the diffraction limit, not at the diffraction limit. And if you look at where Proxima Cen-B is, it's right there. So we think this is a very doable target, and it's a race, because the Europeans did not get permission to do the project with espresso and VLT. But they went ahead, and they're now building a specialized instrument called a Ristretto. That will be ready in 2029, hopefully. We're always late when we build instruments. We're hoping to be ready in 2027. This is a very good thing, because if we had a positive result, we need somebody else to confirm that positive result. If we're a little later, they'll need us to confirm their result. So it's all good for science. And if we don't actually find O2, we will find out whether this technique works at all. We're also going to experiment with resolutions at 400,000. I point out that no one has ever actually injected AO-corrected beam in the optical band into an optical fiber. We'll learn how to do that. We expect surprises, but we'll be ready for the GMT based on that experience. And it's possible that working at, if we can, we're going to go up to resolution of 400,000. It's possible that that extra resolution, as argued by several authors, and particularly Mercedes Lopez Morales, that will help a lot. But again, it's important to try it out on a smaller telescope before we start wasting time on a bigger telescope. And so this plot compares different resolutions of 100,000, 300,000, 500,000 and 1 million. And in principle, what you should see is that the absorption features is kind of a messy plot. Absorption features are much deeper when you go to 300,000 than 100,000. So I don't think I'll skip the HWO JWST concept, but I will say that we are building G-CLEF. This is the shell grating with one of its facets on it. It has all of them on as of yesterday. This is the composite optical bench that took 5 years to build. It's in a box. This is one of the things that will hold the collimator mirror and the spectrograph that was delivered 2 weeks ago. This is the camera system for the red camera that's being tested. It exceeds specification by a factor of 5. There's the collimator mirror. These are my Korean colleagues assembling the calibration system. This is the testing facility for camera lenses. And I'll stop there.
Thank you, Andrew. We have time for questions.
Oh, we want to resolve all that bandhead structure. I mean, that's essential. That's why we know we need a resolution of 100,000. We think that if we went to higher resolution, we would somewhere around 300,000. We're not resolving them out at 100,000. 300,000 we probably would start to resolve, but the individual times, not just the whole.
Thank you for your presentation. So there is a wide discussion on literature about other forms of life. How could we think to a biomarker for other forms of life?
I think my answer to that is that there's a big literature on, could there be other forms of life that are highly speculative, but there's also an experimental component to that question. And so one thing people always think about is, if a certain element, carbon or sulfur in the periodic table, works as a component of biological molecules, what about something that's the next row up? And, why can't you, it's almost the same, why can't you substitute it? Or can you demonstrate it that it can't be substituted? And about 12 years ago, there was this very exciting result where a young researcher was studying a bacteria from Mono Lake in California. Mono Lake is a very salty lake, like the Great Salt Lake, like the Salars up north. And it's all those particular lakes in this region not only have a lot of salt, but they have a lot of arsenic, lots of arsenic. And if you look at the periodic table, right above phosphorus, there's arsenic. And she thought that she found evidence that these were biota that had actually started to use arsenic instead of phosphorus. And this controversy raged for a few years, and I think maybe 2. And then, frankly, a large number of more careful researchers demonstrated that she'd made it was a contamination issue, and that these bacteria were, in fact, all phosphorus-based and did not use arsenic at all. And so there have been a lot of searches like that. I realize that what do they say? The lack of evidence is not evidence of innocence. But people do look pretty hard, and we haven't found. So that we talk about the essential elements being sponge, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, and we've never found any biota that say, well, I'm going to use something else. So that's a starting point. It is the principle of the lamppost. You have a little bit too much to drink, you lose your car keys, you've got to go find them. Well, do you look where you think you lost them? No, you look under the lamppost, because that's where the light is. And so, it seems that water, we haven't found a life form that does need water. We haven't found a life form that isn't involved somehow in oxygen chemistry. I realize that it's just a starting point, but you have to start somewhere.
Thank you. That was a very convincing answer.
I'm not sure I'm convinced, but
More questions?
So this 10 to minus 10 contrast, can you get it all the way to 700 nanometers, or just in the near infrared?
No, that's the thing, is that the Magellan system at this point in time is the only adaptive optic system that works below about a micron. And Laird Close and Jared Males have been visionary in pursuing that. Everybody said it'll only work for infrared. It works very, very well down to H alpha. We did a preliminary study, and then actually one of Claudia's postdocs wrote a paper that made a convincing argument that actually AL could work all the way down almost to calcium H and K very effectively. But we haven't H alpha is enough, good enough for us to start with. But it allows us to do the science we want to do in this arena.
Presentation. About the, well, given sufficient time, couldn't an exoplanet have, well, dark oxygen production at the seafloor? Couldn't it be a false positive of your biomarker?
Are there abiotic channels?
Well, dark oxygen at the seafloor.
Dark oxygen. I'm not familiar with dark oxygen. I'll have to read about it.
Okay, we have a question from the Google Meet. Elizabeth, yeah?
Hi, can you hear me? Elizabeth de Gouveia Dalpino speaking.
Okay.
Very, very nice talk. Can you hear me?
Yes.
Okay. So it was a very nice talk, and I have two questions, two very naive questions, actually. One regards to the fact that you have shown spectra from very interesting, two very interesting systems, but one was a hot Jupiter, and the other example that you gave was this potential candidate, Earth-like potential candidate, but associated to an M star. So my question is, what is the closest Earth to or best candidate as Earth 2 that could be probed by the instrument and by the technique that you are going to apply? So this is my first question. And the second question is, if what about the Earth candidates within our own solar system? I mean, the moons. Can you use the instrument and the technique to do something like calibrate the alternative atmospheres of these Earth candidates within our solar system, so that these calibrations or these observations could be also be somehow used to help to detect and compare with other candidates outside the solar system, further more distant Earth 2s.
Okay, to answer your first question, I'm not 100% certain. I know off the top of my head what is the nearest G2 star with an Earth radius exoplanet. I have to figure that out. As to the solar system, there is no Earth analog within the solar system. Mars is 1/10 of the mass of the Earth. Venus is a similar mass, but has an opaque atmosphere. You might well ask, of the candidates within the solar system that have demonstrable liquid, surface liquid, or large water reserves, which are Europa and Enceladus have subsurface water oceans.
Right.
Titan has surface liquids, methane and ethane, and it's an open question whether Mars has subsurface liquid water. I don't think G-CLEF, obviously for a subsurface probe, G-CLEF is not useful. I don't think, I've never looked at the, we could, I don't think we see methane, I don't think we see ethane. Methane is predominantly a near infrared spectral feature, and subsurface water is not something we can do. So G-CLEF will not be useful, I think, in the solar system context. Does that answer your question?
Right. Okay. Thank you. Thank you for the answer.
Sure.
Okay, more questions? No? Okay. Thank you again, Andrew.